this video, we are going to learn 4 important techniques to solve ordinary differential equations. What are they? Separable equations, homogeneous method, integrating factor, and exact differential equations. Let's start with separable equations. Whenever we have the form of dy dx equals to px times qy, this is our separable equation. Let's see in the real example. Our example is y prime plus 2xy equals to x. Our first step is to convert y prime to dy dx. Let's do that. So dy dx plus 2xy equals to x. Our second step is to subtract 2xy from both sides. So what we're going to get is dy dx equals to x minus 2xy. Now we're going to factor out x and isolate each variables. Dy dx equals to x times 1 minus 2y. If we take out x here, 1 is left. If we take out x here, negative 2y is left. Now our next step is to multiply both sides by dx and divide by 1 minus 2y. I would like to go step by step so you can follow. Dy equals to x times 1 minus 2y dx. Now we're going to divide both sides by 1 minus 2y. So it's going to be 1 over 1 minus 2y dy equals to x dx. Now we completely separated the variables. X terms are on one hand side with dx and y terms are at one hand side with dy. Now we can start integrating both sides. Now we're going to integrate left and right hand side. Integral of x is 1/2 x squared. And we're going to use c on the x term side. Integral of 1 over 1 minus 2y is ln of 1 minus 2y times negative 1/2. If you're fluent with integration of ln, that's great. If you're not, you can do u substitution. Let's do it here. Integral of 1 over 1 minus 2y dy. We're going to call this part of the integral u. So u equals to 1 minus 2y. Then du is the derivative of 1 minus 2y. The derivative of 1 minus 2y is negative 2 dy. And if we solve for dy, we get dy equals to negative 1/2 du. Now let's write everything in terms of u. So it's going to be integral of 1 over 1 minus 2y is our u, 1 over u. Instead of dy, we're going to write negative 1/2 du. You can pull negative 1/2 to the front and keep du here. Integral of 1 over u is ln of u. And we have negative 1/2 in front, ln of u plus c. We don't need c here because it's on the y term side. So negative 1/2 ln of, we have to bring u back, which is 1 minus 2y. So this is the integral of 1 over 1 minus 2y. Or my recommendation is to be more fluent on ln, derivation of ln, and antiderivative of ln's. Let's go back to our main question. Let's recap up to here. What we did at the first step is we call y prime dy dx. At the second step, we subtracted 2xy from both sides. And then we factored out x term. and then we divided both sides by 1 minus 2y, and we started integrating. Now let's continue. So this is our implicit form. Now let's go ahead and find the explicit form. To be able to find the explicit form, we need to solve for y completely. So we need to isolate y. Let's multiply both sides of the equation by 2, negative 2. If we multiply here by negative 2, we get positive ln of 1 minus 2y. And if we multiply here by negative 2, we get negative x squared plus c. So we don't change our constant because it is still constant, so c or 2c is not matter. Now we need to get rid of ln. So we are going to raise both sides to the e. So raise it to the e, power of e, raise it to the power of e. So here our key is e to the ln x equals to x. So e to the ln of 1 minus 2y will be equal to 1 minus 2y equals to e to the negative x squared plus c. We can write this c in front of e. We can apply the logarithmic rules here, so we can do this. That's going to be e to the c as well, and if we merge them, it's going to be c times e to the negative x squared. Again, here we apply the basic logarithmic rules. Now we need to completely isolate y. Subtract 1 from both sides, so negative 2y equals to c e to the x squared, negative x squared, minus 1, and divide both sides by negative 2, so you get y equals to negative c times e to the negative x squared minus 1 over 2. So this is our explicit form. So that's it for separable equations. Let's go ahead and see the homogeneous method. In the homogeneous method, first you need to check if the function is homogeneous. So how are we going to do that? We're going to replace x with kx and y with ky in the original function, and we're going to see if it is equal to original function or not. Let's see in the real example and talk on the solid problem. Let's solve dy over dx equals to x squared plus y squared all over x times y. So this is our original problem. First we need to check if it is homogeneous or not. So we will replace x with kx. So x squared will be k squared x squared plus y squared will be k squared y squared all over. Instead of x, again, we're going to write kx, and instead of y, we're going to write ky. Now, on top, we can factor out k squared. K squared times x squared plus y squared, and on the bottom, k times k is k squared, and xy is left inside. Again, divide the x equals to this. Now we can cancel out k squared. Now you're going to realize that this is equal to our original function, so we pass for homogeneity. Now we can start solving the differential equation. In homogeneous method, this is key. We're going to use the v substitution. We're going to call y over x v, and which is also equivalently 1 over v, or v to the negative 1, will be x over y. Y over x is v, the opposite x over y is 1 over v. So you need to be aware of that. And equivalently, if you solve for y here, y equals to v times x. And the differentiation of this function, if you differentiate y, you're going to get dy dx. If you differentiate this using the product rule, the derivative of the first function, which is dv over dx, times the second function itself, plus derivative of first one times the second one. So if you use the product rule, what you're going to get is dy dx equals to x times dv dx plus v from y equals to v times x equation. Those are the key components that we're going to use in homogeneous method. So you need to be very fluent on this case because you're going to use this again and again. Our first step is, step 1 is always divide all terms by x, because we need the form of y over x, so we need to do this. Let's divide everything by x. So dy dx equals to x squared plus y squared all over x times y. Everything will be divided by x. Actually, we're going to divide here by x squared because our highest term of x is x squared. If we had only x, then we had to divide by x. Since we have x squared as the highest term of x, so we divide here by x squared. So what we're going to get is dy dx equals to x squared divided by x squared is 1 plus y squared over x squared. You can write it in this form over, this is going to be y over x. So second important step is let v be equal to y over x. Now we're going to do v substitution. So this is going to be our v, and this is going to be our v as well. If we had x over y instead of y over x, then we had to substitute 1 over v. Okay, now let's rewrite the equation. dy over dx equals to 1 plus v squared, because we have here square, over v. And in this equation, which is equivalently y equals to v times x, that is our key component, we need to differentiate this function. And if we differentiate this, what we are going to get is dy over dx equals to product rule x times dv dx plus v. Now this v, this dy dx will be substituted with this dy dx. So dy dx is equal to this that we're going to use instead of this dy dx. So x times dv over dx plus v, which we get from the differentiation of y equals to v times x, equals to 1 plus v squared over v. Here, actually, we can separate the function, so it's going to be more helpful. Let's do that. So we can rewrite this function as 1 over v plus v squared over v, which is v. So we use the common denominator and separate. Now we can subtract v from both sides. If we subtract v from both sides, they cancel out. Now the equation is separable. So we need to collect v's in one hand side with dv and x's with one hand side with dx. So it's going to be v dv, because 1 over v goes here as in multiplication. So v dv equals to, and x goes here as 1 over x, and dx goes here as dx. 1 over dx will be here dx, and x will be here 1 over x. Now we are going to integrate both sides. Now our equation is separable, and we're going to apply the separable. The antiderivative of v is 1/2 v squared, and the integral of 1 over x is ln of x. and we use plus c, the constant at the x term side. And we can rewrite this better. So we can multiply both sides by 2. So v squared is equal to 2 times ln of x plus c. Again, we don't need to change the constant. And if you square root both sides, so v equals to plus or minus 2 ln of x plus c. Actually, we need to bring v back. So v was y over x equals to plus or minus square root of 2 ln of x plus c and times x, because we need to multiply both sides by x. So y equals to x times plus or minus x times 2 ln of x plus c. So this is our explicit form, because y equals to function is our explicit form, and plus c is our implicit form. But we need to substitute v back here. Okay. So let's recap. In homogeneous method, the very first checklist is we need to check if the function is homogeneous. And to be able to do that, we need to substitute kx with k and ky with y to see that it's going to be equal to the original function. Then we can start the steps. We divide all terms by x or x squared, the highest term of x. If you have x cubed, then you're going to divide everything by x cubed, because our main goal is to convert it in the form of y over x. And in the second step, we're going to do v substitution. And all y over x's will be v, x over y's will be 1 over v. And we're going to differentiate this equation, which we derive from v equals to y over x. And this differentiation will be substituted with dy over dx. And we're going to simplify the equation and convert it into separable form. So now it is separable. And then we're going to apply the separable equation form. We're going to integrate both sides, and we're going to bring you back the v substitution back. And then this is going to be our implicit form. And this is going to be our explicit form that we solve for y completely. Homogeneous method is not difficult. You need to follow the guidelines, and you need to be very fluent on the keys. And of course, integration techniques are the main frame, the skeleton of differential equations. Now let's see the third method. The third technique we use to solve linear ordinary differential equation is integrating factor. In this method, our function is neither separable nor homogeneous, but in the form of dy over dx plus pxy equals to some function. Let's see in the real example. Let's solve dy dx plus y equals to x. This function is not separable and it's not homogeneous. And it's in the form of dy over dx plus p of xy equals to q of x. If it is not in this form, we put this in this form. Here, we need to detect our p of x. P of x is the coefficient or function in front of y. In our question, it is 1y. So our step 1 is to find what the p of x is. Our step 2 is to find mu of x. Mu of x is the integrating factor, and the formula to find the mu of x is e to the integral of p of x dx, and p of x is again the function in front of the y. So let's find mu of x as our second step. Our q of x is 1 dx. The integral of 1 with respect to x is x. So our integrating factor is e to the x. Now our step 3. This is step 3. Step 3 is to multiply a whole equation by mu of x. Let's do that. Our integrating factor is e to the x times the original function dy dx plus y equals to x. If we distribute, we get e to the x dy dx plus e to the x y, let's write it y e to the x, equals to e to the x times x, let's write it x e to the x. After step 3, the left side of our equation is equal to ddx, mu of x times y, which means the derivative of mu of x times y. So this is the product rule. After the product rule, this is what we get. So this is going to be your check of the function. We're going to rewrite the left side in the form of d over dx, mu of x times y. So d over dx, which is the derivative with respect to x, of mu of x, which is specifically e to the x for this question, times y. The left side after step 3 is always this, whatever the mu of x is times y, equals to x e to the x. Now we're going to integrate both sides. Our next step is to integrate both sides. Here, integral and derivative cancels each other. And what we get is e to the x y equals to integration of x times e to the x with respect to dx. So let's do it here. Integration of x e to the x is integration by parts technique. Differential equations require high knowledge of integration techniques. Let's see how integration by parts is. So we have two methods here. You can either use the tabular method, or you can use the formula, which is u times v minus integral of. So either we're going to go this path or tabular method path. Let's see both of them. Okay, in the formula, we need to define what the u is and what the dv is. So u should be the function which is differentiable very fast, and dv has to be the function which is integrable fast. So after the observation, we can see that derivative of x is good and integration of e to the x is good. So derivative of x is 1 dx, and integration of e to the x is e to the x. Now let's plug in. U is x, v is e to the x, minus integral of v is e to the x, du is 1 dx, 1 times e to the x is e to the x dx. Integral of e to the x is e to the x plus c. So this is the integral after integration by parts. Let's go to tabular method. In the tabular method, we have to define again u and dv. U is the function that we differentiate, dv is the function that we integrate. So what's the derivative of x? Derivative of x is 1. And what's the derivative of 1? 0. So you differentiate until you get 0. Now we're going to integrate. E to the x is e to the x, and integration of e to the x is again e to the x. And Now we're going to make our arrows, and starting from plus, minus, alternatively plus, minus, plus, minus. And we need to stop here because 0 times anything is 0, so it doesn't make sense. Now x times e to the x plus, we have a negative sign here, so 1 times e to the x plus c. As you can see, tabular method is fast and more practical. Now we're going to take this integral and write in our question. So that was x e to the x minus e to the x plus c. And we use the constant c at the x term side. This is our implicit form answer. So this is the implicit form. Now let's solve explicit form. To be able to solve the explicit form, we need to isolate y completely. So we're going to divide all terms by e to the x. So this part divided by e to the x, y alone, divided by e to the x is x left here, divided by e to the x is 1 plus c. Constant, you can keep it in constant, or you can write it in the form of c over e to the x. And this is our explicit form. If you would like to rearrange, you can do this as well. X minus 1 plus c times e to the negative x. You can take e to the x above if you wish. That's it for method 3. Let's go ahead and see the last technique for linear ordinary differential equations. In our last technique, we're going to study exact differential equations. Exact differential equations are the equations in this form. Our standard form is we have m dx, that you can call this part my or m. And this part of the equation you can call nx or n. We have dy here equals to 0. Here, plus sign and 0 is must. So this is how our standard form is. Let's see this example and study the steps. Given 3x squared plus 1 plus 3y squared plus 2y times y prime equals to 0. Steps. Let's observe if it is in standard form. We see that this is not in standard form because this does not look like that. So let's put this in standard form. Let's rewrite everything and convert y prime into dy dx. So 3x squared plus 1 plus 3y squared plus 2y times dy dx instead of y prime equals to 0. Now we're going to multiply the whole thing by dx. So what we're going to get is 3x squared plus 1 times dx plus 3y squared plus 2y. Dx cancels dx here, and we leave dy here equals to 0. Now this is in standard form. We have some function dx plus some function dy equals to 0. It's exactly desired. This part of the function with the dx part, we call it m. And this part with the dy part is called n. You can also sometimes see my and nx. So either way, m and n. Now we know how to identify m and n. We don't have any y terms here, no y terms here. So this is our m, and no x terms here. So this is our n. The reason why we call it my or nx is when we take the partials of this part or that part, we take the partial derivative with respect to y, and we take the partial derivative with respect to x. Now let's go to step 2. In step 2, we need to check if this is exact differential equation. If it is not exact differential equation, we don't need to continue. So how are we going to check if it is exact? We're going to take the partial derivative of m with respect to y, and we're going to take the partial derivative of n with respect to x. And if they are equal, then it is exact. If not, it is not. So partial derivative of 3x squared plus 1 with respect to y is 0, because we don't have any y term here. This is constant, this is constant, so our my is 0. And partial derivative of n with respect to x is 0 again, because we have no x term here, as you can see. So this is constant and this is constant. So nx is equal to 0. Since my is equal to nx, this is check. Our function is exact differential equation. So we can go back and continue step 3. Step 3 is the integration. We are going to integrate only one side of the function, one side of the whole equation, either m part or n part. If you go this path, you're going to integrate m with respect to x, and you're going to add some function g of y instead of constant c. If you prefer to go this path, you're going to integrate n with respect to dy, and you're going to add h of x, some function instead of constant c. Here the recommendation is go observe the original function and pick up whichever part is integrable faster and easier. Here they are equally easy, so let's pick up m part, 3x squared plus 1. So we're going to integrate 3x squared plus 1 with respect to x. And then we're going to add g of y. Let me write it here so we don't forget it. So this is my technique. So I add it already and I make sure I don't forget it. So the way how we solve is totally up to you. Now integral of x squared is x to the third over 3, and 3 cancels 3, so it's x cubed. Plus antiderivative of 1 with respect to x is x. Plus we add g of y. Our next step is to differentiate this function partially with respect to y. Why are we doing that? Because our main aim is to solve for g of y. So if we differentiate this function with respect to y, what we're going to get is the differentiation of this is 0, because there is no y term here. This is 0, no y here. This will be g prime of y. So what we get from this differentiation is only g of y. Now we're going to set this equal to n part of the original function. And what was the n part? 3y squared plus 2y. So g prime of y is equal to 3y squared plus 2y. If you follow this path, then you had to integrate n with respect to dy. You had to add some function h of x, and you had to differentiate h of x partially with respect to x, everything. And then to be able to solve for h of x, you had to differentiate with respect to x and set it equal to this time m part of the function. So whichever half you integrate, you set it equal to other half. And here g prime of y equals to other half, which is n. And we're going to compare left and right side. Since there is nothing to here subtract or add, that's clear as desired g prime of y. So this step is automatically done for us. Now we're going to integrate both sides with respect to dy, because we want g prime of y to be g of y. So we integrate both sides. Integral g prime of y dy equals to 3y squared plus 2y dy. G prime and integral cancels each other, so we have g of y here. And 3y squared becomes y cubed over 3. 3's cancel out, so y cubed is left. plus y. Antiderivative of y is y squared over 2. 2's cancel, so it becomes y squared here. And some constant k. So be careful not to use c here. Use k, other constants, or you can use c1, c2. Now let's go to the next step. Since we have g of y here, this g of y will be substituted to, and this is our fxy. So our fxy is equal to x cubed plus x plus, instead of g of y, we're going to write y cubed plus y squared plus k. Now we're going to substitute fxy with c. C equals to x cubed plus x plus y cubed plus y squared plus k. And if you merge this constant k and c, which is going to be c minus k, is again constant, so you can keep it as it is. X cubed plus x plus y cubed plus y squared equals to c. We were given some function, and we observe it, and we would like to see if it is in the form of m dx plus n dy equals to 0. And here, plus sign and 0 is must to check for standard form. And the x part of the function, we call it m, and dy part of the function, we call it n. And in some sources or in your school books, you might see my and x as well. And as the second step, you need to identify m and the n part of your given equation. At the m part, you don't have y terms. At the n part, you don't have x terms. And our next step was to check if it is exact differential equation. So we take partial derivative of my with respect to y. That's why we call it my. And we take the partial derivative of nx with respect to x, and we compare it. If they are equal, then our function is exact. If it is exact, we can continue. Our next step is to integrate. We integrate either m part or n part. So either way is okay. Here we went through m part. If you integrate m part, you integrate it with respect to x and you add some function g of y. If you go this path, you integrate n with respect to dy and add h of x. Then you differentiate partially with respect to y to solve for g of y. Or you differentiate partially with respect to x. And you set it equal to other half of the original function. So if you integrate this part, you set it equal to this part of the function. If you go and integrate n part, then you set it equal to m part at this step. And after this step, you compare left and right side, and you make clear g prime of y equals to, or h prime of x equals to some function. And next step, you integrate both sides because you need g of y alone or h of x alone. And what you get is your implicit solution. And don't forget to set it equal to 0. So instead of fxy, write just 0. This is totally up to your teacher or the book you use. And here I have shown shortly how c is derived. Now let's go to our bonus. Our bonus is some standard integrals. It's going to be very helpful to know some standard integrals. So I call them back pocket integrals. So I have added ln, some exponential functions, trigonometric functions, inverse trigonometric functions, and hyperbolic functions. So you can copy them and memorize. And this is also a fast technique to find derivative and antiderivative of trigonometric functions. So if you go to clockwise, you get the derivative of each trigonometric functions. And cosine